Hello everyone, we are back now to talk about convolution neural network with PyTorch. So we saw a convolution before where you look at how to do transformation in the images, and then we look at the neural net itself without convolution on top of it, and now we are going to put all together in a CNN or a convolutional neural network model. So this example we're going to be running using Collab because we are going to be training our model, and this will take some time if you're running on the CPU, and I don't have a GPU here on my machine, and therefore we are going to use Collab. That's the best option for that. So when you click on that button here, you're going to open your notebook straight in Collab, ready to run. I've already run it here to speed up things, and we first thing, when you are here on the Collab, you should choose to change runtime and make sure you are using GPU, and that's it. So basically you can go and run all cells, or you can run one by one. Okay, we are going to be working with the CFAR10 dataset. It's a very known dataset of images of 10 categories. So airplane, automobile, bird, cat, deer, and dog, frog, horse, and sheep, and also truck. And that's our 10 categories that we'll be working with. And this data set will be downloading from this location here on Amazon, and this part here will download the data set. Here will be the extracting the file, and then we will be do some transformation here, so you can see all the categories that we have in our train and test data set. So first time we are going to be looking a little bit more about our data set and how we structure things and how we read stuff. On the first part we were kind of ignoring this because we are more focused on the understanding other part of our puzzle. But now the data that we are downloading, it is data here, that is data, and you're saying it's CFAR10. And when you are working with convolution neural network, we separate our image usually in two folders, one for train and another for test how our model it's being performing. So, and inside each folder we will have different folders with our categories, and that is how we are labeling our data set. Okay, everything inside this folder will be airplanes, and therefore will be already, when you are reading this data, we are going to see those images labeled as airplane, and the same for the others. Okay, see, we are reading all the folders inside train, which it is our classes, and then you can see all the classes here. We are looking at airplanes and checking some image that we have inside the airplane folder. And on this part here, we just look at the ships. Then we start to read our data input as in a data set, and then we use this TensorFlow PyTorch function, let's say a util function that will just read from an image, and automatically you'll be taking all the folders as the label for our image. And here you can see one example of data set, and we can see the shape, which it is 22 by 22, and you have a channel of 3 because it's a color image, and the category label is 0, and 0 it is airplane. Okay, and then you can see here a tensor, as we already saw. So it's RGB values for each picture, and you can see that is 3-dimensional array, as we were seeing before on the NumPy, but now it's a tensor object. And here you can see the classes, that's our classes, and then we plot some example. This image, it is done especially for let's say test purpose, and therefore the image is very small and very low quality, and because it will speed up the training, so it's very good for let's say to test and to teach neural net. So you saw one example here of a plane, and you can see another example of a plane here as well. This is, you cannot see well, but it's a helicopter, looks like. And then we're gonna start to prepare our let's say model, and we starting splitting basically our data set in two, which will be training and data into validation. And so we chose here, again, is not new, but we chose the size of the batch, and then we put everything in a train data load and validation data load. So in data load, it's just preparing our data to be loaded in our model on during training. We are going to be looking at data model later when we are working with multi task model, and you have to create our let's say our custom version of data load instead of being using the PyTorch one. So then you're going to learn more how that works. So we're going to skip that for now, and as we always do, we separate things and go deeper on each element, and data load is not time yet. Okay. So here, just to show all our data, it's a very just a util function, and here we show our data. So in one batch of our data, right? And then we'll define you're going to define our model. So again, we just a recap of how convolution neural network works. And as we saw, we have our kernel, and that will be sliding through all the pixels and generating new values. Okay? And on data flow on PyTorch, we use this function with convolution 2D, and you're gonna see more about it down here. So that's how we create. So we're creating a convolution layers, which will get three here. It is our channel, which basically our three colors that we showed before, and here 8, it is the output of the layer, and this would be also the z, the dimension of our three-dimensional array. And basically we'll be creating 5 different versions of our image. Basically is 5 different filters, those that we saw before when we were doing convolution. So would be generated here as one map, feature map. We call those as feature map. And kernel, that's those that we were seeing. So here we're using 3 by 3, and stride, it is how we want to slide down the kernel. So basically this is what's doing here. It's 1 by 1, but you could just skip 2 if we want as well. So you can choose stride. This basically the size of the step. So you can choose 2 or 4, but here we do 1 to go through every pixel. And so we did that. Then we did max pool as well, something that we saw previously. So here, that's how we do max pool on using PyTorch. So again, and that's we create a new model with two layers, okay, one convolution and a pooling. And now we are gonna see how it behaves. You can see we're gonna see each layer output and the final result of this model. Let's see down here. Here I'm just getting the first batch of image from our data load. That's how you get it. So image and labels, and now we're going to use those image and apply our layers individually. So you see, you have convolution layer, which we basically created here, and have pool. Okay, and we also have our simple model. Remember, I created a simple model with 2 layers, And that's all, just two layers with one convolution and pool, and you're gonna see those individually output. So that's, and we apply our simple model with those two, and then we apply layer by layer here, and we store our output, and then we're going to be looking at each output. Okay, this was not a very good example, quite bad example. Try to load one different one. Okay, I'm gonna run this again to see if we get another image example, because this one's not good. Okay, very good. We need to reload. I'm gonna reload again. It's good to see, because then if you face issue like that, you'll be able to fix it. So I think I need to run everything again from here. Run after. See. It's running everything again, and here in our example we have, which image is that? It's a cat. It's a cat image. A cat image was not the best example, but let's talk about that anyway. So this is original image, and you can see that the image with a filter, that's one image with another filter, it is a bit blur here. This one it's a bit more transformated, and here also a bit different. So every output here, it is one okay, I think it will be good to look at. So for example, when you there you go. So that's our original image. So it's a cat, and that's the original image, which have 128, which is the size of our batch. So that means that 128 images on this tensor, and 3, which it is the colors, and here's the size of the image. Okay, then we get our convolution output, which we did up there, and that will be still 128 images. However, we now have 8 channel, and that means we have 5 extra channels on our 3-dimensional array. Okay, so we had 3. That one was green, red, and blue, and now we have 5 more, which are those 3 examples I'm showing here, but I have 2 more others, and with the same size, right? That's, and then we have the pool output, which it is have the same, but now you can see that the size was reduced by half. Okay, and just going back and remember what we're talking about here. So we convolution only, and here output, and then the model. Let's see how the model it is now. The model output, which contains both, will have 8 channels and half of the size of how it was in the beginning. Okay, so you can see each layer output being performed, and this is this value 8 here came, just remembering where it came from. It came from our model architecture, which you say that will be 8, but if you put like 50 or whatever, it would be more channels with more filters and more version of our image. Okay, and here all together individually we are looking at each output. I hope that being clear here what happened on our multi-layer stuff, multi-layer model, and we were now look at the image to try to understand it better. And our model, it is compounded by input image, convolution layer, which you saw there, and pooling, and then you'd have another convolution layer plus pool, and then we'll do a fully connected layer. So we stopped here just because for example it will be the same, continue to be the same, just creating other layer. You're gonna see down below. And the important thing that we have to keep in mind, it is that fully connected from here, down, it would be the same what you have been seeing, right? So up to here it's new, and that's the convolution part of CNN, and from here forward it is what a neural net that we have been seeing, and we created our own from scratch and everything. So when I show the rest of our model, I think that will make sense. So we're gonna bring it back here and talk a little bit more about that. So then we create our image classification base, which it is basically will be used by any other model that we create will be creating. So don't need to do this again and again. And here it is everything that we already saw, right? So we got the batch, do a forward, let's check the how measure our loss with a cross entropy function, and you see how far from the good result it is, and recalculate. So basically this step training, this is the validation step where we're going to measure how our model is performing, and here you get the final by epoch, and here also part of the measurement thing. So this is our base. So now here we are using, this is basically programming skills that to be using. So you are creating let's say a parent class which will be using by other class, more specific objects. Okay, so now we are using our base class, and now we are gonna be focused on create our model for CFAR10 model. Okay, and now remember you saw this already, and up down here you saw in the previous lesson, and here again another convolution and ReLU and max pool that you saw as well, and then you can see that it is let's say done the same and the same and the same, and up to here it is the flat. So this is the convolution part, and here you can see that we give 3 channel, and the output will be 32, then 64, and then 128 and 256, right? And then we end up with flat. Then we're gonna be flat everything and basically apply what you have been seeing, that it's neural net. Okay, this part here, everything here, it is our convolution part, and from here will be our simple neural net, let's say. And you can see that our image is reducing every time it's 8, 4, but is that, remember that this is not our small only data that we have 260 256 let's say dimensions with different data, and in the end we flat every data that you have into one single in a 2-dimensional array. Or no, actually you get only 1 dimension in the end of in the end of everything. So here we are creating many let's say dimensions, and then we flat everything. And here what flat means, right? Remember our model output, which had 5. I think we can, let's I'll show it here. So let's see the shape. This shape is 128, 8, 16, right? But when we flat, that's what happened. 20, just one single data with all the data that we have here, like 1 in one single one. So this 128 image is still there. You see that I took this the first image. For every image we have all this data built, or for every image we had 8 versions of our image. Okay, and that is what we are going to be will be the input to our neural net. And when you transform all this image in one single value, that's become exactly what we had before. Remember this here, it is basically taking this guy and do each convolution that we have used, right? 1, 2, 3, 4 layers, and we end up with this amount here, right? So you could just replace this by this one here. And remember that on our version, we had our input size here, like the size of this image. Remember, what is this input size coming from? Yeah, so it's the size of the image, 28 by 28. It is the same that we are having here, but now the image is bigger. And then you just apply what you have been doing so far: linear relu, linear relu, and linear relu, and it's basically that. So that's our architecture. And then we have our convolution. Then we feed on a simple in a simple neural net and expect the final result. Then we can see our model, how it is. You can see here when it's already there. So with all the layers for our model, and then you can start. Then we're gonna try to predict. Let's see what is there. Oh yeah, then you try to predict image, then you get the prediction before training, and that would be pretty bad. And then here it is just for the data load. Data load still now, but now it's in the GPU. And here we do our training. Remember our batch load, train step, and backward, the same thing we have seen already. And here is our validation phase, and we put our model on a GPU as well again. And then we start our training. Now we are calling fit, not train anymore. It's just because fit it is more the standard for PyTorch. So it is, we don't add this step as part of the model as we were doing, but instead we just create a function and pass the parameter for this function. This way you will not have to be changed. This will be always the same function, and not to have to create for each model that you're creating, duplicate everything. So just the small difference. Then basically after the training, we plot the performance. So you can see the start very bad here, and the accuracy going up and up as the epoch increases. We do as well with the losses. So we start the loss very high, and then you will see that in some point here, that's an important concept you're gonna see. It is that in some point our model is not learning anymore, so it started the validation. It started to go up again as it was in the beginning. That's called overfitting, and that's a very important concept in the convolutional neural network or deep learning in general. Overfitting, it's when you don't have enough data to let's say generalize your model to let's say be able to predict different example of data. And that we'll talk a little bit about this here. And we identify overfitting when you see that even though your training error is going down, the accuracy of the prediction is going up. So basically it is getting worse as more interaction it's being added. So to fix those, you need to basically get more data, or let's say transform your data to be more generic. So you can kind of rotate, you can change colors, and so on. You can see more about this topic in this in a very good website, or examples that this guy have put together. So this is going to be applying batch normalization and dropouts, and this should be very important, and you should be looking at this. So now let's test our model. So we read again from our testing folder, and then we create a function here to predict it quickly, where we're looking to the data to our classes, get the prediction, put on our class, and get the right name. So that's it's our data, our image, and then we pass here to predict, and then we get the right label and the prediction. So our label is airplane and the prediction it's airplane, and the image you can see here that it's look like airplane. Cannot really really tell. And another example here we have again, now it is automobile, and you can see that's automobile, that's the label, that's the what you predicted, and that's it's what you had as the image. And we also have here frog. We predict a frog, and we can look at the occurrence as well, so we get more data and evaluate all together. And you can see that we have a 76% occurrence on our data. We can also, so after all done and get our final let's say model, we can just save our weights, and here we're saving a CFAR10 CNN, and we can create another model. We are creating here another model and just loading the data from the one we have saved, and then you are able to test again with the model 2 here now, and you get the same as a percentage of the same occurrence. And that's how we do. So we do all the work up to here, save, and then distribute this file, the widget here, across to other application to just load it and start use on your app. Right? So that's it. This is to introduce a little bit about the CNN part of our model. So we saw that on the previous part we look at from the fully connected layers, but now we have introduced the convolutional layers on top of our neural net, and we could look at each layer output individually and see what it's being output on those, and the final result as well when you put all together on our final model. We have also introduced this new way of structure our layers using a sequential function from PyTorch, where you can kind of organize our layers in a better shape, different from what we did on the previous lesson, what we wanted to simplify as much as possible to help you guys to understand. Yeah, that's it. I hope you have enjoyed and have learned about CNN, and see you next lecture.